Good morning, everyone. Today, I will introduce the homework tool number 4, closed loop control system. We will cover 3 major areas. First, fundamental principle of the feedback control. Second, the time domain performance index used to evaluate the system timing's behavior. Includes daily time, rise time, peak time, overshoot, and setting time. And third, a practical self-motor control system that implement closed loop control in industry. What is a closed-loop control system? A closed-loop control system, also called a feedback control system. What is a controller system in which the output of the system is continuously measured and feedback to the controller. The controller then compares this measured output with the desired input and adjusts its action basis on the difference to minimize any deviation. This slide assesses the core principle of the closed loop control, the feedback loop. The diagram shows the signal flow, starting with a reference input. It compares to the measured output via the feedback pegs. The result arrow signal is processed by the controller to generate a control action for the plant, which products a new output. It's continuous cycle of measurement, comparison, and regression, minimize error and exhaustion stability. It is important to understand the difference between open loop and closed loop control. Open loop systems are simple and cheap, but they lack feedback, make them inaccurate and sensitive to changes. Think of the toaster. It cools for set time regardless of the actual toastings. Closed loop control system, on the other hand, uses feedback to continuously adjust and correct, making them highly accurate and robust. This comes at the cost of increases complexity and space, which is why they are used in present applications like robotics and manufacturing. We know about the figure 1. Figure 1 shows the unity step response of a typical automated second-order closed loop system. We use 4 keys. We use this four key domain index to evaluate its dynamic behavior. First, daily time. TD is how long it makes the response to first half of the final value. Second, rise time. TR is the time to go to from 0 to 100% of the steady state value. Third, peak time. TP is when the response research the first measurement overshot. NP is how much the peak exceeds the final value, so as a percentage. Together, TD, TR, and TP measure response speed, which MP measure how much the system oscillates. Settling time, TX, is the moment when the response enters and stays within a certain percentage ranges of the final value. Two standard tolerance hams are commonly uses 0.05 means plus or minus 5%, which is more relaxed and widely used in engineering and engineering. 0.02 means plus or minus 2%, a stricter standard for high percentage applications. Naturally, the smaller tolerance ham, the longer the setting time. On the right, the formula for Meissner overshot MP is shown. Is equal the output at peak time minus the final value divided by the final worth times 100%. MP is diamond sensor legs. A dart map MP means more oscillation and worse relative stability. The figure 2 shows a practical self-motor closed-loop control system. The signal flows start with a common signal or set point going into the controller or PLC. The controller sends control command to the serve driver, which contain a power state and inner current loop. The drive then powers the servo motor, which drives the mechanical load. Secondly, an encoder mounted on the motor shaft continuously measure the actual position and speed. Its mirror signal is feedback to the servo driver as the feedback signal. Inside the drive and controller, the actual output is compared with the design reference input. If the actual position lags behind the target, the drive increases motor output to reduce the error. Its closed-loop matrices automatically compensates for load variation, friction, and disturbances, allow the motor to correctly check reference commands. Okay, that's all. Thank you for your listening.